Okay, in this lecture, we will study the steepest descent method, the first method in our plan, which uses the gradient. Okay, so Cauchy's method, the steepest descent method, selects the direction of the negative gradient as the direction of line search in every iteration. And as you know, through the point xk, the current point xk, if you pass a hyperplane, which is the tangent plane of the contour through that point or level surface through that point, then that is orthogonal to the gradient. And the gradient is orthogonal to that level surface outward, that is away from the minimum. And inward from that level surface or the tangent plane at that point, any direction that you take is a descent direction, because their direction and the gradient have a negative inner product. And the rate of descent along the direction is basically the directional derivative of the gradient. And that directional derivative of the gradient is negative in an inward direction. Okay, making an obtuse angle with the gradient. And its magnitude is basically the cosine of that angle. Okay, so that will be best if you take the direction as the negative gradient, in which the entire magnitude of the gradient will appear as the directional derivative. For any other direction, the directional derivative is only an orthogonal component. So that is why in steepest descent method, the direction is chosen as the negative gradient. Okay, so along that direction, the function decreases fastest, at least locally. Okay, and so we know that at the starting point of the line search, the gradient, the negative gradient, is orthogonal to the level surface. At the end of the line search, if it is an exact line search, then there it will be tangential. So along the same direction we are proceeding for line search, and the level surfaces from the start of the line search to the end of the line search actually turn through right angle. Okay? So this much we know in the background. Now the algorithm, which is very straightforward, you select an initial point and a few parameters, usual parameters, the maximum number of iterations, tolerance on the gradient norm, gradient magnitude, and tolerance on delta f in any iteration. That is, with how much improvement in the function value you will consider that it is still not converged. We have to go. When the delta f in an iteration turns out to be less than this tolerance value, then you will say we have converged. Okay, or at least there is no more hope of improving further. That means after that, very little improvement, which is inconsequential, will take iterations and iterations, which is meaningless. Okay. Alternatively, rather than taking a tolerance on improvement in function value, you could have taken a tolerance on movement in the solution space. It would be an alternative. Or you can use a combination also. Now, with this much preliminary work, you start the iterations. And iterations have very straightforward steps. Evaluate the gradient. If its norm is extremely small, then stop. We have already converged. Otherwise, take its negative or the normalized negative as the search direction, line search direction. If you take the normalized negative, then the direction vector will be a unit vector. Otherwise, it will have the magnitude of the gradient. I mean, it's all right. You can do that. After selecting the direction as this normalized version or the full, you conduct a line search by whatever method you choose, golden section or whatever. And that basically means minimize this with respect to alpha, positive. And you get the line search result, alpha k, where this gets minimized. And then move up to that in this direction. So basically it will turn out to be xk minus alpha k gk, right? Because dk is simply minus gk or its normalized version. And now you check if in this iteration enough improvement in the function value has taken place. If not, that is if it is smaller than the tolerance, then that means there is no need to continue further and you can stop. Alternative to this, as we discussed, you could have used this kind of a condition, okay, or you could use a combination. Now, after you complete this and come out, you should check whether the number of iterations exceeded the limit that you have put. I mean, if the exit was forced or exit was because of convergence, that you should check. Okay. So if k is less than m, that means exit was normal. It was not forced by this maximum number of iterations, and the result is reliable. Otherwise, it would mean that it has been a premature exit. It has not converged. So in any algorithm, wherever you put a limit on maximum number of iterations, after exit, you must check this. Okay. Now, these values, what values you would check, you would put, that typically depends on the scale and quantities of the problem involved. What value, what change, what value you would consider as small enough, large enough, and so on. So that for that, no rule can be specified because these things typically will have their units, and m, the maximum number of iterations, that will depend upon the level of complexity of the function that you are minimizing. Okay. Now we need to know the convergence properties of the algorithm. It is clear that the function value at the next iterate will be less than the current iterate because we are taking a descent direction, in fact the steepest descent direction, and conducting a line search. So line search is a very reliable step. So in that the function cannot increase, and function cannot stay constant also because it was a descent direction and you are doing a line search. And in line search, there is no chance of overstepping because you would appropriately reduce, and then stop somewhere after which you don't want to reduce further or cannot reduce further. So if the function is bounded below, has a minimum, then through such steps, it will always approach a minimum point and therefore global convergence is guaranteed. In how many iterations it would do that, that is not known, and that is a matter of local convergence. So far as global convergence is concerned, it has excellent global convergence. In fact, it is very reliable and exemplary so far as global convergence is concerned. We will spend more time in analyzing its local convergence. So started sufficiently close to a minimum point, at what rate the algorithm approaches it. Linear, quadratic, superlinear, whatever we want to find out. So sufficiently close to X star by Taylor series, you know that you can represent it locally by an appropriate quadratic approximation in which the Hessian will be positive definite. Okay, because it is around a minimum point. So, and not only a quadratic function, actually this quadratic function qx, which is the general form of the quadratic function, can be shown to be equivalent to this function, which is in a way an error function. If you take x equal to x star, then this is 0. Okay. And you can show this because qx minus ex, just subtract these two. The quadratic terms in x are equal, so they cancel out. Linear terms from here b transpose x and from here x star transpose ax, they come together and make this, which is 0, because if x star is the minimum point, then this is the gradient, which is 0. Okay, gradient of this, right? So this is 0. So the linear part is also 0. And what remains is constant. C minus half x star transpose A x star. So two functions differing by a constant will have their minima maxima, the full profile together. One will be just lifted and so on. Okay. So any quadratic function can be put in this form. So fine. So rather than analyzing it on the actual function, we analyze it on a quadratic function, which is a reliable model in the local neighborhood of the minimum. And rather than analyzing it on this, we analyze it on this ex, which is another quadratic function differing by a constant, equivalent. Okay. So now, on this quadratic function, as we try to analyze the local convergence with a positive definite, we construct the gradient. Make note that our intention will be to develop some idea about this error function at xk plus 1 divided by this error function at xk, because or its powers. Okay, so that is how we talk of rate of convergence, convergence ratio, etc. So that is why we are organizing it in this manner. So we evaluate the gradient of this, that is simply a times xk minus x star. Differentiate it, put x equal to xk. And at xk plus 1, the gradient would be similarly this. And if you use this gk expression here, then you will get a times xk minus x star plus a times xk plus 1 minus xk, which is this. So gradient at xk plus this extra term. That is the gradient at xk plus 1. Now in steepest descent method, direction is minus gk. I mean, if you are using normalized version, then you can develop a parallel analysis which will go at the same point finally. Now, so xk plus 1 is this, which is xk minus alpha k gk. Okay. In place of dk, you have put minus gk. And then here xk plus 1 minus xk, you see, that is minus alpha k gk. So put here minus alpha k gk. Then gk plus 1 is gk plus a times minus alpha k gk. That is this. And from the condition of exact line search, for which we develop theoretical results, dk transpose this is 0. That is, whatever is the direction, at the end of the exact line search, the gradient will be orthogonal to that direction. Okay. So here dk is minus gk. So equivalently, we can say this. Or using this expression of gk plus 1 here, we will have gk transpose gk minus alpha k gk transpose a gk. That is this. From here, basically, we get the expression for alpha k, the line search result. And you see, for a quadratic function, line search result is analytically available if you know the matrix A. Okay, because for a quadratic function, you will typically know that. So based on the gradient, you can find this. Now, this turns out to be the expression because it is steepest descent method. Negative gradient is the direction. In any other direction, also, you can work out an expression like this analytically. So for quadratic function, you really do not need the actual line search to get it. For a general function, you need that. Now, this alpha k expression we will use. And a few other things also for which we do these notations. to make our analysis a little crisp. Okay, for brevity. So this xk minus x star we call yk. So this gk turns out to be a times yk. Okay, smaller expression. Yk will turn out to be a inverse gk. And exk, which is this, will turn out to be half yk transpose ayk. So we have got an expression, a crisp expression of E at xk. Now we'll develop another expression for E at xk plus 1 and then divide. So E xk plus 1, that is xk plus 1 is here, minus x star, xk plus 1 is here, minus x star. And xk minus x star we have decided to call yk. So get that here, and the remaining things remain. Now multiply this out and you get this. And now use these two equations which we just now developed. Gk is ayk. Here it will become gk. And so this whole thing will become gk transpose gk multiplied with twice alpha k. Alpha k supplies another gk transpose gk. So gk transpose gk whole square divided by this. That is actually this. Twice minus 2 here. And here, when you put this alpha k expression, then gk transpose a gk in the denominator twice. One gets cancelled with this, the other remains. And in the numerator, gk transpose gk whole square comes, which is the same as what you got from here. That is why minus 2 times this and plus once this. So together it is minus 1. Okay, and this term comes. Now this is E at xk plus 1. Next iterate. And now divide. And that is convergence ratio for a linear rate of convergence. Okay. And we find that if we divide it by E at xk rather than any other power of it, then only we get this finite ratio. You see, E at xk is this thing. So we divide by 1. Okay. Half of this thing, half this thing. So half goes, this goes, 1 comes here, this comes here. Okay. 1 minus this stuff. And we notice that by dividing it with just e to the power e of xk rather than any power of it, we get this expression as finite. So that is why we say that its rate of convergence is linear and convergence ratio is this. Here, some gk is coming and some yk is coming. We can simplify that by using the expression of yk in terms of gk, a inverse gk. So in place of yk, we put a inverse gk here also, and then gk transpose a inverse a. So that goes off, and we get this. Okay. So this is the expression for the convergence ratio. First of all, the rate of convergence is linear, so we are not very happy. We would be happier if it were better than linear, happiest if it were quadratic, and so on. Okay. And now we are interested in examining how good or how bad this convergence ratio is. If the convergence ratio is something like 0.1 or 0.5, 0.1 or 0.05, 0.08, then we would be happy. That would mean that in every iteration, we reduce the error so much that only 10%, 8%, 11% error remains. Okay. On the other hand, if the convergence ratio turns out to be something like 0.9, then we would be unhappy. That means most of the error remains. Okay. So we would see how bad or how good this convergence ratio could be. So for that, we have an excellent result called Kantorovich inequality, which is actually a linear algebra result, not necessarily connected with steepest descent algorithm or optimization. It says that if A is a symmetric positive definite matrix, then for any vector, you have this result where lambda max and lambda min are the greatest and least eigenvalues of A, both positive, make note. Okay. So to establish this result, You first consider the orthogonal diagonalization of the matrix A. That is possible because it is symmetric, and all the eigenvalues come into play. So after using the orthogonal diagonalization, you put this expression for A, the corresponding expression for A inverse, and Z, the vector, also you represent in the basis V as V times vector W. Okay. So then this will be W transpose, V transpose V, W. V transpose V is identity, so that goes off. So here it will be W transpose W whole square. Here this whole thing will become W transpose lambda W. This will become W transpose lambda inverse W, and so on. So the left hand side will immediately reduce to this. Why we said reduce? Because here this lambda and this lambda inverse are diagonal. And then since these are diagonal, so we can quickly open that in terms of the components of W. So this is anyway sigma Wi square, okay, whole square because of this. And this is, as you conduct this product, you get sigma lambda I Wi square. This product will give you sigma 1 by lambda I Wi square. Now this sum of Wi square, two of them are here. With one you divide here, and with the other you divide here. Okay. Then here also in place of Wi square, you will get Wi square by the sum of all of those. Here also you would get that. And that thing, Wi square divided by sigma Wi square, if you call xi, then this entire thing would reduce to 1 by sigma lambda I xi, this, and here sigma 1 by lambda I xi here. And because of this definition of xi, you have these conditions. That is, each of them is non-negative and all of them are together 1. Okay, it's a convex combination. And now we will use a consequence of convexity which we saw in our earlier lecture on convexity. That is, for a lambda broken in several lambda i's, lambda 1 to lambda n, in a particular manner by taking xi coefficients, which are like this. That is, by breaking a given lambda as a convex combination of n known values of lambda, we get the maximum value of the sum, the corresponding convex combination of the function values of a convex function psi, when the contribution here and here comes only from the two extreme points, that is lambda min and lambda max. That is, other than xn and x1 when all the x's are 0. So look up your old material on convexity lecture, you will find this. Okay. So that old result on convexity we now apply here on the convex function 1 by lambda. Now you see this 1 by lambda is here and lambda is known. Okay. So when you put that lambda, the question is, how do we break it in several components, x1, x2, x3, x4? So this thing, which is this sum, will be maximum when you take only the components from the last two elements, lambda 1 and lambda n, lambda max and lambda min. Okay. Then this will be maximum and therefore the fraction will be minimum. So typically LHS would be greater than equal to the case when you take that. And that is what we do here. Okay. So applying this on the convex function, sigma I, psi lambda, 1 by sigma, 1 by lambda, this thing